All right, my friends, welcome. So my name is Filip, and this is a session about one of the most fascinating topics, I think, in all of modern technology, and that is quantum computing. So first of all, thank you for coming. I really appreciate that you are here, especially as Hanselman is speaking in the other room right now. Also, it is the end of this day, and I think it is quite challenging to expect to sit through an hour of quantum physics at the end of a long day. But hopefully we can make this interesting. My idea for this session is to not do a standard sort of introduction into quantum computing, because there's quite a lot of material online about this. But instead, I had this idea that perhaps we can walk through some of the more bizarre quantum mechanical concepts and sort of look at them through the lenses of quantum computing and the Q-sharp programming language to sort of establish a base that is then useful in learning quantum computing in the future. As I mentioned, my name is Filip. I do have a last name, but nobody can pronounce it, including me, so I typically just say Filip W. They actually booked a hotel for me as Filip W as well, and when I came yesterday, they didn't want to let me into the hotel because they said there's no booking for me. And so the usual stuff, blog and all these other things that you would expect. I am a Microsoft MVP in the quantum category, so this is a new category in the MVP program that was established recently. I also recently wrote this book, so this is one of the first Q-sharp books on the market. Technically speaking, it is not yet on the market because it will start shipping in about 3 weeks. It's actually in print right now. So if you're interested in the contents of this session and you want to follow up, then I would recommend you this book because I really like the author. And this is the company that I work for. It's a company based in Switzerland. It's actually based in many places, but headquartered in Switzerland. And if you are maybe interested in moving to Switzerland, then let me know because we are hiring. And the motto for today is going to be this great quote from Richard Feynman, who famously said, "I think I can safely say that nobody understands quantum mechanics." And of course, Feynman himself got the Nobel Prize for his work on quantum theory in 1965. So we will start by having a very quick introduction into Q-sharp, the quantum development kit, and the Azure Quantum. And that will sort of set the stage for the rest of this session. So I have it actually timed. I had a card somewhere, but I lost it. It was timed. I was very well prepared, actually. It was timed to take exactly 8 minutes. But I usually start talking about nonsense and then it all goes away. So now I don't have my card anymore. Anyway, so what is Q-sharp? So Q-sharp is a programming language that is quantum specific. So it is actually developed for the purpose of quantum hardware. It is not a general purpose programming language, but it can only be used with quantum hardware. It should be somewhat familiar to .NET developers. So if you have .NET development background, at least the tooling will be familiar. It is not a .NET language because there is no .NET for quantum hardware, but sort of, development experience is similar. So you develop in VS or in VS Code, you use .NET CLI to compile your program, you use NuGet for package management, and you use MS Build for project, for managing the project files. It comes with a family of libraries, so this is not just the core standard library of Q-sharp, but there are actually domain-specific libraries. That's why it's called QDK. And finally, you get access to local simulators, so you can simulate up to a certain complexity level the programs locally, or you can run, of course, on Azure Quantum. Now, from my perspective, what I would say is that the amazing thing about the Q-sharp, the QDK, and Azure Quantum is that it sort of gives you very easy access into the quantum ecosystem. And in many aspects, this is actually mind-boggling because about maybe 5 or 10 years ago, in order to be able to interact with quantum hardware, you probably had to be a researcher or a PhD student at a really good university. Right? And now all you need is just an editor and access to the internet, and you will be able to run some simple things, of course, because the current generation quantum hardware is actually quite basic and it cannot be used for a lot of useful things. But in many aspects, quantum hardware or quantum computers are some of the most complicated machines that have ever been built by the human mind. And so being able to sort of access it directly from your machine is quite amazing. Here is an example of a Q-sharp program. It is, or it's not even a full program, it's just a single operation. The point here is not to discuss what is going on deeply. We will actually have time for that later, but this is just to familiarize yourself with the syntax, right? So this is defining an operation that generates a random number. It will return an integer, and what it does, it allocates 16 qubits. And the qubit is a basic unit of information in quantum information science. And in many aspects, it is similar to the classical bit. in a sense that we can only encode a 0 or a 1 into a qubit, and we can only decode a 0 or a 1 out of the qubit. But during the program execution, the qubit can also enter a superposition state, which then sort of gives the program certain possible quantum advantage. And so in this case, we are actually going to be creating a superposition here using the so-called H operation, which gets applied to every single qubit. Again, we will discuss this in details in a moment. Then information, classical information, has to be extracted or has to be decoded from qubits, which happens in this case through a measurement. So there is a measurement applied. This multi-M operation actually performs a measurement of every single qubit in the qubit array. And it returns a classical array of bits. And in this case, we would return, or we would convert this classical bit array into an integer, and we get a random number. The important thing about this is that this is really a true random number in the sense that it is underpinned by the laws of nature, right? So on a classical hardware, there is actually no way to create a truly random number. Everything is just an approximation. And this is actually underpinned by the laws of quantum mechanics. So Azure Quantum, few words about Azure Quantum. Well, it is there so that you can run your Q-sharp programs, of course. It might be that in the future also other languages will be supported. It gives you access to simulators. So locally you have simulators with the QDK, but on Azure or in Azure Quantum, you have actually access to hardware-specific simulators. So at the moment, there's actually no universal design for quantum hardware. So each vendor has its own sort of a technology to implement quantum hardware. And therefore, not entire API surface of Q-sharp is available when running on different hardwares. And therefore, having a vendor-specific simulator is very helpful. Now, of course, you can access real quantum hardware as well. At the moment, there are two hardware providers in Azure Quantum. One is called IonQ, and the other is called Quantinuum. Both are startups that are building quantum computers using the so-called trapped ion technology. There is no first-party hardware from Microsoft yet, but it is not unreasonable to expect that this will happen in the future, that Microsoft will have its own hardware as well. And you get free credit, so at the moment you get actually $500 just to play around, which is useful, of course. And the way it looks like, if I jump to Azure Portal, you actually see this service called Quantum Workspace. So this is in public preview, so everybody can use it. And so you can just jump here and create a new one. I actually created one for the session. And effectively what it does, it creates a workspace for you and a backing storage. And in here, you would see which providers you have access to. And as I mentioned, so there is quantum hardware from IonQ and from Quantinuum. There is something called Microsoft optimization, but we will not be talking about this today. And here we will see actually that we do have IonQ QPU. So this is the moniker for the quantum computer from IonQ, and there is an IonQ simulator. And because, of course, the resources are quite scarce, you could see that there is currently a 12-minute wait time. If we submit something to an IonQ quantum computer, there's an average 12-minute wait time for it to be executed. And then if you look at the job management here, these are all the jobs that I have in the past submitted to this particular workspace. And you can always download the output of this. And the way you'd interact typically with Azure Quantum is to install a quantum extension for the AZ CLI. And once you have your program, you would submit this program to your quantum workspace to a specific target ID. And the target ID is this moniker that is seen here. Oops. That is seen here. So like IonQ.QPU would tell Azure Quantum to execute this on the IonQ quantum computer, and so on. And once it's submitted, you actually get the job ID back, and you can use this job ID to query for the status of the job, and ultimately to fetch the output. The way the hardware works on Azure Quantum at the moment is that you are actually expected to return some sort of a binary output, and this binary output is then made available to you when you fetch the outcome of the job in the form of some sort of a histogram. So typically, a lot of quantum algorithms, in fact, most of them are probabilistic. So you typically want to run your program multiple times and then see the possible outcomes. And architecturally speaking, this is how it works. So once you have an Azure Quantum Workspace created, you would use the QDK to submit your program to Azure Quantum, which really uploads it to storage. then it gets queued for execution on a specific provider, so specific hardware or specific simulator. And once it runs on this provider, you can always query for the job status and ultimately download the output, which will be written back into Azure storage. We will see all of this in a moment, but this was just a super quick introduction and a sort of high-level explanation of all the pieces that are in place. We are now well positioned to start talking about the core topics for today, which are really the most troubling or most interesting quantum concepts and how they relate to quantum computing. So the first one is superposition. And the best way to describe or discuss superposition is to actually look at an experimental setup that is called the Max Gender Interferometer. And this is a common experiment in optical physics, in quantum physics as well. And it consists of a light source, which is in the bottom left here. And so that is typically a laser, and two detectors, which are seen on the right-hand side. And in the middle, we have a number of optical elements, and the light is emitted from the laser, it travels through the optical elements, and it is detected by detector 1 or detector 2. So I will now actually annotate this so that it makes more sense. But effectively, what we know is that, we know that light is a form of an electromagnetic radiation, and this has been known since the 19th century. So we can actually explain everything that is going on in this diagram, because here light is emitted from the light source and all the light actually is hitting detector number 2. So we can actually explain everything that is happening here without invoking any quantum physics, right? So let's do this. So light is emitted as a wave from the laser, and it travels as a wave. This is supposed to be a wave, but it travels towards the first optical element, which is called the beam splitter. And as the name suggests, the beam splitter will split the beam of light into two beams of light. There is nothing particularly controversial about this, because we have all seen a beam of light being split into two beams of light. I will mute my phone because somebody's messaging me. So basically, two beams of light now travel here and here, right? And these are mirrors, so they just reflect the light. So light now travels along this path and along this path. And because light travels at a constant speed, and because the distances here are actually fixed and the same, the two beams of light will meet at exactly the same moment at beam splitter number 2. Now, the sort of, let's say, I would say either logical or naive way of thinking would be to think that, okay, this is a beam splitter again, therefore it should split the beam of light again into two beams of light, and light should be detected by detector, or should travel towards detector 1 and detector 2. But that is not what is happening. And the reason why it's not happening is because of the interference effect. And interference is a common behavior that is exhibited by all kinds of waves, including waves on the surface of water, right? So two waves, when they meet, they can create a bigger wave, or they can cancel each other out. And so effectively, because of interference, what happens is light only travels towards detector number 2. So this is, everything here has been known already in the 19th century. So there's actually no quantum concepts that we have invoked yet, and everything can be explained without any problems. But it's only once we start digging into the quantum domain where the problems start appearing. Because we know that light behaves like a wave, or electromagnetic wave, but we also know that light is made of particles. This was shown by Albert Einstein in 1905. He actually got his Nobel Prize for this work, right? That light is made of particles, the so-called quanta of light, or as we call them, photons. So it was not the theory of relativity that he won the Nobel Prize for. So now let's imagine that we turn down the intensity of the emitted light so far that we are able to emit individual photons, right? So what happens when we emit a photon? Well, a photon travels towards the beam splitter. And now, by definition, photon is indivisible, right? So we cannot expect it to sort of split the same way as the beam of light. So the logic would tell us, the common sense would tell us, that it has to go one way or the other only. And it doesn't seem like it's a huge problem, because if you think about the beam of light, it's made up of many, many photons. So if some go this way and some go that way, then things should average out, and we should still have the beam splitting behavior happening, right? So let's go with this idea. So let's imagine that the photon, this particular photon, went this way, right? So it goes to the mirror, it reflects from the mirror, and it approaches beam splitter number 2. And this is where the logic breaks down. Because we already said that, well, if we expect that the photon will randomly go this way or that way, we should now have the same behavior with the beam splitter number 2, that it randomly goes this way or that way, right? So it should sometimes go here, and sometimes go here. But what this experiment shows that even if we emit individual photons, they still only arrive at detector number 2 ever, right? So it turns out that the common sense explanation doesn't work. So we need a quantum explanation. The quantum explanation tells us the following. The photon approaches the first beam splitter. And at this point, it sees that it can go this way or that way. And so it goes both ways, right? So it enters the superposition state, and it goes this way, and it goes this way, right? And then it goes this way from the mirror towards the beam splitter and this way. And now it is approaching the beam splitter from 2 different directions. So a single photon, right? And so it ends up interfering with itself, the same way as the beam of light was interfering with the second beam of light. And because of interference, it sort of localizes itself here, and it only ever triggers detector number 2, right? So this is extremely bizarre, because the only way we can explain this experiment is by saying that the photon is actually in 2 places at once, that it enters the superposition state, and it is able to be in 2 places at once. We can very easily model this in Q#, actually. And we can model it in the following way. We would allocate a qubit as our photon. Then we would use the H transformation as the beam splitter. This is the same transformation that I mentioned earlier in the random number generator. We will look at the details of this operation in a moment, but for now we'll just use it. Then we have a second beam splitter, so this is a second H operation. And then we need to model the detectors somehow. And the way we can model the detectors is to perform a measurement. As I said earlier, the only way we can extract information out of a qubit is to perform a measurement. So we would measure the photon. M is a built-in operation for measurement in Q#. And the measurement can only produce a 0 or a 1, which we can then, I mean, this is our program, so we are free to map it to detector 2 or detector 1. And in this case, if we run this program, which we will do in a moment, we will actually get the deterministic result. It will only ever produce a 0 as a measurement result, and it will only then print out detector 2. So we managed to recreate the experimental conditions. But it is very weird, right? Because, again, the only way we managed to explain this is by saying that the photon takes both of the available paths at once. But it actually gets weirder. Because if we say that the photon is in 2 places at once, well, why not just enhance our detection logic and try to detect the photon in those 2 places at once, right? And this is actually shown here. So this is an enhanced experimental setup. What we now have is we have these additional detectors here, these black ones. These are called the so-called quantum non-demolition traps, which, without going into details, they are able to detect photons as well. And so here's what is happening. Let me annotate this again. So the photon is emitted from the light source. It reaches the beam splitter. At this point, we said that it will enter the superposition state. And it travels all the way here, and it encounters our detectors. So we tried to outsmart the photon. Like, a small photon is just a particle. It's pretty dumb, right? So we can outsmart the photon. So we put up 2 detectors, right? So we should now see both of those detectors flash at the exact same moment, and we should be able to catch the photon in 2 places at once. But as it turns out, that is not what is happening. So when we try to outsmart the photon will actually outsmart us, because the photon will randomly say, I'm here or I'm here. So it will actually randomly trigger one quantum non-demolition trap or the other. And this will happen really with 50% probability. So they will randomly flash. And as one of the detectors flashes, then the photon really becomes localized on a given path. So let's say here. Now it approaches the beam splitter from one path only. So the superposition state has been destroyed. So it doesn't have itself to interfere with anymore, right? And because it doesn't have itself to interfere with anymore, and because it is no longer in the superposition state, well, what happens in beam splitter number 2? The same thing that happened in beam splitter number 1. Namely, it will enter a superposition state. So it now travels here and here, right? And now it is approaching both of the detectors, right? And now what will happen in those detectors? Well, the same thing that happened with the quantum non-demolition traps. They will randomly flash. So the photon will, again, we will try to detect it, and it will only show up either here or here. And these detectors will be flashing randomly. And the reason why this is amazing is because the photon actually behaves differently depending on whether we look or not look. Right? And this is in strict contrast to classical physics, where there exists an objective state of a system that can be measured as an experimental outcome. Here, by simply changing our way of observing the photon, we change the outcome of the experiment. Again, we can very easily model this in Q# by using the earlier code and simply adding an extra measurement in between the two beam splitters. And in this case, it's the same measurement that we had at the end here, except we will map this to quantum non-demolition traps 1 or 2. And notice what is happening here. The photon enters a superposition through the H transformation, and then it's measured. And when something is measured that is in the superposition state, it will produce a random result. Then again, a superposition state is created, and again we perform a measurement, which again produces a random result. And this is this concept of a superposition. We are now in position to actually run this in the code. And here I have exactly the code that I had on the slide. So one operation is called the Max Gender operation, and the other operation is called the Max Gender with quantum non-demolition traps. So this is exactly the same code that I had on the slides. This is my Q# program. And by the way, Q# programs have QS extension. But interestingly enough, the project files are just CSproj files, so they actually pretend to be C# projects. In fact, if you look at the project file, they are actually pretending to be .NET 6 application, and the only thing that makes this quantum is this quantum SDK that is included, which actually under the hood will wire in the Q# compiler, and the Q# compiler is then able to detect that there are QS files and compile them. So this operation will run, and I can actually run it as a .NET Run because the QDK also wires in the default simulator into the .NET Run command. So this operation will run the first variant 10 times and then the second variant 10 times. And notice what happens. In the first variant, we only get detector 2, the same as we were expecting from the experiment. In the second variant, where we have quantum non-demolition traps, we get random results from the quantum non-demolition traps and random results from the detectors. And really the only difference is that here we let the two beam splitter operation, so 2H operation, to be happening in a row, whereas in the other case, we had the extra observation in the middle, right? So let me show you something else. Let's now have a look at the random number generation code that we also saw on the earlier slide, because now I think it will make a bit more sense. So what this code does, it will allocate 16 qubits and then create a superposition for every single one of them, right? And because, as we mentioned, when something is measured and it is in a superposition state, it will randomly produce a 0 or a 1, which effectively means that, for each of those 16 qubits, we produce a random 0 or a 1, which, when sort of stitched together, gives us a random 16-bit integer, right? And this is effectively how it works. So if I now run this again runs on the default simulator. At this point, it just gives me a random number. And if I run it again, I should have a different random number. Or I'm super lucky maybe, and it's the same. We can submit this to Azure Quantum. And the way we could submit this to Azure Quantum is to use the AZ CLI. But we will have to make a small modification in this program. So this is a variant of this program that is runnable on Azure Quantum. So the difference here is that in order to make this easier to read, I change it to a 4-bit or 4-bit random integer, which is really a number between 0 and 15. And instead of sort of reading out the integer in memory, what we are returning is the measurement result, which is a result array, which is really a bit array. So it actually says here that this is an array of zeros and ones. And this is then returned as the output of the entire program. This is a current limitation of Azure Quantum, so we need to have this binary return from our program. And the way I can run it, I have a command here that will allow me to do this. So it will be so we can submit jobs. This is what is typically done. But for simulators, we can just tell directly, please execute, and that would wait for the execution, right? Otherwise, it's asynchronous, so it just gives us the ID back. And so it should take about 30 seconds, I think. We should be able to see here in the jobs that there is something going on. Yeah, so it's still submitting, so that's fine. In the meantime, I can show you something else. So the one other change that I needed to make in order for this to be submittable to Azure Quantum is I needed to add an execution target ionq.qpu. And as I mentioned, these quantum hardware implementations, they are somewhat limited at the moment. So for example, if we tried to read the measurement result into memory, what we would see here is we would get actually a compiler error, and the compiler would say that this requires full computation capability, which is not supported by IonQ processor, right? And that is what I meant by, okay, that we have to actually submit, or we have to have a program that returns a binary output. And what the simulator tells us is the following. It tells us that when running this program, these are the possible outcomes, right? We are going to generate a random number between 0 and 15, so a 4-bit integer. And it tells us that effectively each number between 0 and 15 is equally probable to come out of this, right? And so with a probability of 625. So this is, again, this is underpinned by the laws of nature. So what I can now do, I can actually submit this for execution on a quantum computer, which is actually the next command here. And we can check what is the wait time. The wait time currently is 12 minutes on average. So we will come back actually. So once it's submitted, we'll actually come back to this in a moment. So we don't have to see the results straight away. Whoops. What happened? So somehow I managed to lose the screen. Let me plug again. Maybe something here. Oh, it's back. Good. Good. There's superposition. So what we got back is we got back this job ID, right? And so we are able to actually query for the output here. And this is now waiting. So I do not expect that this will be completed yet. But we can anyway try to fetch the output. And it should give us an error. And so, exactly, so there's no result yet. And we should see it actually being queued here. So see, this is actually here, and it says that it is waiting. So we'll come back to this later, so it doesn't matter. But what is important is that at this point, we are actually well positioned to introduce a little bit of theory. So for simple so-called two-level quantum system, so a qubit is a two-level quantum system because it can only represent a 0 or a 1 or a superposition of both. Then for such systems, quantum mechanics prescribes that the state of such a system is described by a two-dimensional state vector, okay? And quantum mechanics also tells us that information from quantum systems can only be extracted by the so-called observables, okay? And each observable defines two special vectors, for two-level quantum systems at least, two special vectors that form the so-called measurement basis. So whenever we were measuring a qubit, like we were doing in our Q# code, we were actually using a specific measurement basis. And the default measurement basis in quantum information theory, and in general in all implementations of quantum computers, is the so-called Z basis. And it consists of two vectors, very simple vectors, 1 over 0 and 0 over 1, which can be used to map to a classical 0 and a classical 1. They are, in short, they are called cats. So these symbols are called cats. And cats are just a shorthand way to indicate that these are vectors. So we call them cat 0 and cat 1. And the default qubit state happens to be cat 0. So whenever our program starts, we know that it is in state cat 0, which really means it's in this vector state. And here is something fundamentally really, really important, right? The basis, the two states that are defined by the measurement basis, or really by the observable, are in principle the only things that are possible to be observed in the measurement process. So in other words, there exists no objective reality, right? So we cannot ask a quantum system what state you are in. We can only ask, are you a cat 0 or are you a cat 1? So we say, we have selected the Z basis for your measurement, which consists of two special vector states, cat 0 and cat 1. Please tell me which of these two states you are. And that is why a system in a superposition ends up producing at the end a random number upon measurement, because it randomly chooses 0 or 1, right? It actually chooses ket 0 and ket 1, but we map them to classical 0 and classical 1. The problem is that the quantum system may be in the state ket 0, or it may be in the state ket 1, but it actually may be in the linear combination of both of those states. And that is expressed by a simple equation, alpha ket 0 plus beta ket 1. Now consider when alpha is 1 and beta is 0, we have a state ket 0. If beta is 1 and alpha is 0, we have a state ket 1. But if both of them are non-zero, then we have the so-called superposition. And in fact, there is no one single superposition. There are infinitely many superpositions. And we can draw this on the circle. This is not a perfect visualization, by the way. It should be actually drawn on a sphere. But it helps to sort of comprehend this better. So we have a state ket 0 and state ket 1, which are vectors. And these vectors are linearly independent, so there is 90-degree angle between them. And really, any state in between, like this red arrow, for example, is a superposition state. And it is an allowed state of a quantum system. And a quantum system might be in any of those states. And if the system happens to be in the state ket 0 already, so it perfectly aligns with the vector ket 0, then upon measurement, we get a deterministic result. We always get a 0 out of a measurement. But if the state of the system is a superposition state, any of those superposition states, the outcome of the measurement is probabilistic. So we would say that the superposition state collapses to one of the observable states. And that is actually, I mean, it cannot be emphasized enough, because it is a fundamental quantum doctrine that a measurement of a quantum property does not reveal the value of this property, but instead the value of this property sort of comes into reality as a result of the measurement, right? So, in other words, what we experience in the world is sort of a projection onto the observable states only, but the true nature of reality is sort of inaccessible to us. And as Anton Zeilinger said, the world is not as real as we think, right? We can add some mathematics to this now, and effectively how we would represent the H transformation. So when we take a default qubit state, which is a ket 0, it is a vector 1 over 0, and the H transformation has the following matrix format in quantum mechanics. Now, every quantum transformation can actually be represented as a matrix, because that is just in linear algebra how we transform vectors, right? By multiplying them by matrices. And when we do this calculation, we end up with something like this. And this is, notice, alpha and beta are both non-zero, right? And what is more, alpha and beta are actually equal to each other, which tells us that the resulting state is exactly in the middle between ket 0 and ket 1, which means there is a 50% probability of observing a collapse to ket 0 and 50% probability of observing or measuring a collapse to ket 1. In other words, that is why we are able to use the H transformation in our random number generation, because it is a perfect quantum coin toss. And even more amazingly, if we apply H twice in a row, something interesting happens. Because when we multiply H by itself, we end up with a matrix that looks like this. And this is the identity matrix. And the identity matrix doesn't actually change the state of a vector. So in other words, H is its own inverse. So applying it once will create a superposition. But applying it the second time will actually undo the superposition and return the qubit or a quantum system back into the original state. And that is why in the earlier example, when we had two H transformations applied in a row, we ended up with a deterministic result, because the first beam splitter was creating a superposition, the second one, through the interference effect, was actually undoing it. Now, the problem is, of course, how to interpret all of this. And the ontological character and the epistemological character of all of this is actually unclear and has been troubling physicists and philosophers for almost 100 years. And already 100 years ago, Niels Bohr said that there is no quantum world, there is only an abstract quantum mechanical description. And so, in other words, we have a mathematical model that works amazingly well and is able to predict the outcome of all these quantum phenomena. But actually, what does it mean in terms of the true nature of reality? We don't know. Another concept I wanted to show you is the uncertainty principle. And this is related. So in order to actually discuss this, we will introduce a different measurement basis. This is called the X basis. And it consists of two different vectors. And they are typically called ket plus and ket minus in quantum information theory. They still only are possible to be mapped to a 0 or 1. So it is effectively a different way of encoding or decoding a 0 or a 1 into a qubit. And similarly as before, when we perform a measurement in the x basis, we can only ask a quantum system, are you a ket plus or are you a ket minus? Nothing else, right? And the best way to think about this is to actually look at the experiment, which we don't see very well because of, I think there is a resolution problem. Skaliert. Oh, like this. Perfect. So this experiment is called the Stern-Gerlach apparatus. Okay, and so what happens here? We have an electron source, and electrons are being fired onto a fluorescent screen. The electrons are fired onto a fluorescent screen through an electromagnetic field. And electrons have an intrinsic property called spin, which is a form of an angular momentum. And it's very interesting because they form, spin is a two-level quantum system. Spin can only have a value +1 or -1 in a given spatial direction. So for example, vertically it can be spin up or down. Horizontally it can be like spin plus or minus, which is really +1, -1. So it can only have two values in a given direction. So now imagine that we prepare electrons with the spin up, and then we fire them from this electron source. And when they travel through these two magnets through the electromagnetic field, the orientation of the magnets is such that the magnets effectively perform a Z-basis measurement, because the only thing the magnets can do is deflect the electron up or down. And because the spin was prepared up, the magnets are actually measuring in a compatible basis, because the only thing the magnet can do is deflect up or down. So it actually deflects all the electrons up, and this is what we see on the screen. Now, if we prepare spin down, it's the same, right? We prepare a spin that is compatible with the measurement. So this is equivalent to preparing a qubit in a state ket 0 or ket 1 and then measuring it. In that case, we will always get a deterministic result, 0 or 1, because we measure in the basis that is compatible with the preparation. However, we can rotate the magnets, and by rotating the magnets, we are now measuring in the x basis. So the only thing the magnets can now do is deflect left or right. But the electrons are still prepared with spin up or down, right? So the basis measurement is effectively asking the electrons, is your spin left or right? Is it ket plus or is it ket minus? Well, it's neither, right? So the electron randomly chooses, well, it will be left or it will be right. And we get random results, right? And we can very easily model this in Q#, and we can model this by allocating a qubit. We can always flip a state of a qubit from ket 0 to ket 1 using the X transformation. This is like a classical knot. It takes ket 0 to ket 1 to ket 0, and then we measure. And so far, when we were measuring anything, we were implicitly relying on the Z basis. This is what happens when you perform a measurement in Q#. It just implicitly uses the Z basis. But the measurement can also be done in a parameterized fashion, so we can choose the measurement basis. In this case, if we choose the Z basis, we get a deterministic result. We prepared ket 0 or ket 1. The Z basis defines the basis states ket 0 and ket 1, so we get deterministic result. Otherwise, we will get random results. And this is effectively what is happening in this code. And this is the uncertainty principle. And uncertainty principle tells us that in quantum mechanics, there exist the so-called conjugate variables that we cannot know values of with arbitrary precision at the same time. Okay, so this might say, okay, well, spin, who cares about electron spin? But there are other such uncertainty relations that are really the fundamental rules of quantum mechanics. The most famous one is the position and momentum uncertainty, which at the high level tells us that if we know precisely the position of a quantum object, we don't know how it is moving. And when we know how it is moving, we don't really know where it is. And even more dramatically, there is the energy and time uncertainty. And the energy and time uncertainty can be best explained by thinking about empty space or an empty region of space. This is a beautiful visualization, by the way. So imagine an empty region of space, and we remove all the matter, all the energy out of it. It's really true emptiness, right? And so what is true empty? That's void, right? That's the definition of void. And if I would ask you what is happening in the void, well, the logical answer would be nothing. But as it turns out, this is what is happening in the void, and these are so-called quantum fluctuations. Because of the energy and time uncertainty, it turns out that if we shrink the time unit far enough, we have such amazing, precise knowledge of time that we completely lose all the confidence in energy. Normally, we would know there is zero energy in the void. So we shrink time unit far enough, and now we lose all the confidence in energy. And it turns out that at these tiny scales, the so-called virtual particles can appear out of nowhere, like literally out of nothing, without any source of energy, like God moment of creation, like they just appear. And then they immediately destroy themselves. And by destroying themselves, they release energy. And this is really the energy that they used to create themselves in the first place. So they sort of borrow energy from the future, and then they pay it back. And this is really absurd, and it sounds like science fiction, but we can actually detect this. There's something called the Casimir effect that is actually, or that makes it possible to detect this. So we know this is happening. And we have good reasons to believe that this played a very important role during the Big Bang, and maybe even contributed to the Big Bang itself. But going back to quantum computing, uncertainty relations or uncertainty principle means that the Z and X basis measurements are not compatible with each other. They do not commute. In other words, if we measure a qubit in the Z basis, this creates maximum uncertainty for the measurement in the X basis and vice versa. So Einstein hated it, right? So he famously said, God does not play dice. And apparently Niels Bohr responded, Einstein, don't tell God what to do. Here is a way to think about this. Again, this is not a perfect visualization, but hopefully this will help. So I will annotate this again. Imagine a quantum state that looks like this. Now, we already said that this is a superposition state when we look at it through the Z basis. But now notice what happens in the X basis. Now, the same state is actually here. And it is a known basis state in the X basis, right? So if we measure this in the X basis, we get ket plus always as a deterministic result. So what happens to be a random thing in the Z basis is actually definite thing in the X basis. So now imagine we measured in the X basis and it actually collapsed to ket1. If we now continue measuring in the Z basis, we will forever get ket1 as the result. But ket1 is actually in the middle here with respect to the X basis. So as soon as we switch back to the X basis, we have a superposition state in the X basis, which then will randomly produce ket plus or ket minus. This is sort of a way to think about this. And this is very important because it tells us that superposition is actually basis dependent. And as it turns out, this is very important because it allows us to encode information into a quantum computer in a specific way. And the information can only be decoded if you know which basis was used to encode it in the first place. So this is like security that is built into the very fabric of reality. There's something called the BB84 quantum key distribution protocol. And it is a protocol that defines how two parties can securely exchange an encryption key over a public channel, which sounds like it's not possible, right? So the way it works is that Alice would generate a random sequence of bits. And of course, it has to be much longer, but this is how many I can fit on the slide. She then proceeds to encode those bits into qubits by randomly switching between the Z and the X basis. So how she would encode data into, or how she would encode 0 into the Z basis by creating a state ket 0. How she would encode 0 in the X basis by creating a state ket plus. Then 1 in the Z basis would be a state ket 1, and then 1 in the X basis would be a state ket minus, right? Then she sends all those qubits to Bob over a quantum communication network, some sort of a quantum fiber link, but it doesn't have to be secure. Then Bob receives those qubits, and he would like to decode information out of it. But how can he do this? He doesn't know the bases that Alice used. So he will randomly switch between the bases as well. So he will be effectively guessing. And statistically speaking, he will guess 50% of them correctly. So what Alice and Bob can do, they can communicate over a public channel and just compare the bases that they used. They would then throw away all the values that correspond to the bases that were incompatible, and they only keep the values where they use the same basis to encode and decode information. I think I have here a mistake because it should be 1, 0 in the beginning, but doesn't matter. So that is the point, right? So now they have a shared key, right? And it should be much longer. Now the problem is that maybe there was an attacker here in this communication link. Now, it turns out that it is not so easy to attack a qubit because arbitrary quantum state cannot be cloned, and this we already said. The only way we can extract information from a qubit is to apply an observable, which really means performing a measurement in a specific measurement basis. So if the attacker doesn't know the basis, well, he has to guess the basis and perform a measurement first. There's just no way to copy a qubit. And so the attacker needs to guess the basis, right? And by guessing the basis, the attacker will actually, I mean, some of them will be correct, some of them will not be correct, right? And in the cases where the attacker guessed incorrectly, it would cause a quantum state collapse that would then generate a mismatch between Alice and Bob. And so what Alice and Bob can do, from the remaining bits, which now should be identical between them, they can take half of them and compare them. And if there is any mismatch, then it means that there was an attacker in the middle and they have detected an attacker. And the protocol prescribes actually that if the attacker is attacking every single qubit, then there will be a 25% error rate on the protocol. And in fact, we can look at this protocol in Q#. I have it actually implemented in Q#. We will not go through all the code because it is like 160 lines of code, but it is implemented sort of in process in a Q# program here. And it really goes through all the steps that we discussed. So Alice will randomly choose her bits and randomly encode those bits into qubits with random bases. Then there is an attacker. Then Bob will randomly choose the bases, will measure using those bases. Then Alice and Bob would reconcile, so try to compare the bases used. And ultimately, there is an eavesdropper check. We can actually run this just for the sake of running this. And we should be able to see that the protocol actually works. And it is actually invoked here twice. The last parameter here is the eavesdropper probability. So in the first case, the attacker always attacks. In the second, it doesn't attack at all. And notice what happened here. In the first case, actually, there was a 25.2% error rate. And therefore, the eavesdropper was detected. In the second case, there was a 0 error rate. And Alice and Bob now have the same key. Now, again, this sounds like science fiction. But it is not, right? This has been actually used in production. For example, I came from Switzerland. In Switzerland, some years ago in Geneva, there were local elections that were actually secured using this protocol by a company called Swiss Quantum. The Chinese researchers, they actually have a quantum satellite in orbit. So they are able to run this protocol through a satellite. And they actually did this between a ground station in China and a ground station in Austria. And this was actually sort of the longest distance for this protocol that was ever achieved. Okay, the final concept I want to show you is entanglement. And entanglement is probably the most bizarre of all of them. And so here we have two Stern-Gerlach apparatuses, one on the left, one on the right. And what we are doing, we are emitting an electron, or actually two electrons, a pair of entangled electrons. And one goes one way, one goes the other way. Here, the measurement apparatuses are drawn very closely to each other. But in principle, they could be at the opposite ends of the universe even, as long as the entanglement is preserved. So what happens is one electron travels one way, one travels the other way. And we perform a measurement of them. And in this case, the measurement is done in the Z basis because the magnets can only deflect up or down. And notice what is happening. The result is random, but it's always perfectly correlated. So if one measures to down, the other measures to down. If one measures to up, the other measures to up. And if we switch the measurement bases, it's the same, right? So the measurement outcomes are actually perfectly correlated with each other. Always. And we can very easily reconstruct this in Q#, allocate 2 qubits, create entanglement. There is actually an operation built into Q# to entangle 2 qubits, and then we measure them. And as long as we measure in the same basis, the measurement outcome will always agree. And of course, we could also send one of the qubits over a quantum communication network somewhere else, and then we measure them separately, and the outcome will always be the same. This is entanglement. It doesn't seem like much, but it is something that completely destroys our understanding of the true nature of reality. Why? Well, we already said that a single qubit can be described using an equation like this, right? So alpha ket 0 plus beta ket 1. This is a single qubit, or a single two-level quantum system can be always described like this. Now for a multi-qubit system, so once we have 2 qubits or more, we actually need a tensor product of the individual state. So the second one will have its own alphas and betas. And if a single qubit can collapse to ket 0 or ket 1, it is not unreasonable to say that once we have 2 qubits, well, they can collapse to 0, 0, 0, 1, 1, 0, or 1, 1, right? That is how our random number generator was working, really, right? So we had 16 qubits, and each one collapsed to a 0 or 1, but sort of as a composite system, they collapsed to one possible solution for this entire system, right? So it sort of makes sense to think about this way. The problem is that this works for independent qubits, but actually breaks down for entangled states. The the equation for the entangled state that we were using in the experiment looks like this. And it looks very much like a superposition state after the application of the H transformation, except it spans across two particles or two qubits. So it effectively says that there is a 50% probability that both of them will measure to 0 or both of them will measure to 1, right? The problem is these two equations are not compatible with each other. So we cannot find the alphas and betas to actually satisfy this equation, right? We will not need to go through this, but I can challenge you, and maybe you'll find them, but it's not possible. So what this tells us is that we cannot decompose an entangled quantum state into a product of the individual quantum states. Or in other words, and this is really, really bizarre, is at the quantum level, or what the quantum mechanics tells us, is that the smallest possible unit of reality is now this entangled state consisting of the two particles or two qubits. They simply do not exist as independent entities anymore, right? The only way we can treat them is together. But the problem is, we can send one of them this way and one of them this way. This is what is happening in the experiment. So they can become spatially separated, but quantum mechanics still tells us that they are one thing. And because of that, when they are measured, they acquire a random value, but it's always the same. So it seems that they are communicating instantly. And Einstein hated it as well, and he called it spooky action at a distance. And this has been experimentally tested in many different ways. And it is really like this, that they seem to be randomly collapsing to a certain value, always in a coordinated fashion, and as if they were in an instant communication, faster than light, right, so superluminal. And so that is why Einstein hated it. And he actually spent a lot of time searching for the theory that was called the local hidden variables theory, that would effectively explain this. So what Einstein assumed, and this was actually a very logical assumption, that what we perceive as a random measurement outcome in this case is actually pre-encoded into this pair, right? So they are predetermined already to which value they would collapse. But he never found the solution to this. And in 1964, at CERN in Geneva, John Bell came up with a brilliant mathematical method that became called the Bell's theorem, that actually proved that the correlation exhibited by quantum objects is stronger than anything that can be pre-encoded into this pair. We will not go into the details, but it effectively meant that the theory that Einstein was looking for cannot simply exist, because anything that you would pre-encode is not strong enough to actually reproduce the correlation of those objects. And this is related to the fact that these objects can be always measured in infinitely many bases, right? There's actually infinitely many bases that we can choose. So there's just no way to pre-encode infinitely many bases, information from infinitely many bases. But this is a bit beyond the scope of this session. And we call this non-locality. So it sort of tells us that at the quantum level, let's say the notion of space and time is not really what we experience at the macroscopic level. And Henry Stapp called Bell's theorem the most profound discovery of science. Now we can actually use entanglement in a Q-sharp code. And so here is an example of this. So we already saw a random number generator, and we saw a quantum key distribution protocol. And this is effectively both of them collapsed into one. So we would have two sets of qubits, in this case 8 qubits for Alice and 8 for Bob. They would become entangled with each other. And then each one, so both Alice and both Bob, will actually read out a random number. And they are going to be guaranteed that this number is the same. So this is like quantum key distribution together with a random number generation. And you could imagine that at this line 19, of course, in this case, it all happens in one program. But at this line 19, they can actually go their separate ways. They can just take their qubits, in their qubit storage and just go away. And at any point in the future, if they measure and the entanglement is preserved, then they are guaranteed to acquire the same random number. And they are guaranteed to be in the possession of the same key as their counterpart. And this happens without any sort of a space-time communication anymore, right? So they don't even have to be online to do this. Like they can just hide in a cave and measure at one point, and they will be guaranteed that their counterpart gets the same value. So we can run this. We can run this actually on the simulator first. And if I run it, it uses 8-bit integers, so numbers between 0 and 255, and it runs 100 times this protocol. And it will compare the values, right? So you can see this is what is produced. And there is 100% agreement between Alice and Bob, so they really get the same number, right? And we can actually submit this to IonQ as well. Here is a slightly modified variant of this program that can be submitted to IonQ. So instead of reading out an integer, we are reading out a binary representation of this integer, and that is being returned from this program. So that is just that. So we can actually submit this to the to Azure Quantum. I will run this on the IonQ simulator. It will be a bit faster. So as this submits, we can actually check what happened to our earlier submission. So we submitted this job to the IonQ Quantum hardware, and notice that it came back. And actually, the probability distribution that we were expecting was something like this. So this is, we were generating earlier a 4-bit random integer, so a number between 0 and 15. And the simulator tells us that each of these values is equally likely to come back. Now, when I submitted this program to Azure Quantum, it actually ran 10 times. So we got 10 different values, right? So actually, 7 of them are distinct, and then this one, and if you can read binary, yeah, I should have been better prepared. So this one came back 3 times. And this is normal, right? Because that's just probabilities. And so if we run this more and more time, it would sort of converge towards the expectation values that that the simulator returned. And of course, this is not much. This is just 10 random numbers. But in many aspects, it's quite amazing because we managed to submit it and run it on a real quantum computer. And that is really a device that maybe 20 years ago was only theoretical, that we didn't know that it could exist. And now it is just available to us for sort of playing around. And here is the final thing. So this is what we submitted now to the simulator. And notice that it comes. So this was the random number generator that uses entanglement. And notice that it still reports to us that there are 16 possible outcomes of this program. And the number for Alice and the number for Bob is always going to be the same. That is effectively what this is telling us, right? So there's still 6.25% probability for each outcome. And the values for Alice and for Bob are guaranteed to be the same. And I think this is everything that I had. If you would like to see the slides, they are actually a website, so they can be viewed in a browser. The demos are all on GitHub, and there's a link here to the book that maybe if you are interested in that might be a good read. And all the photos that were used today are actually coming from CERN, from the CERN public outreach program. And I think that is it. We had a bit of technical problems, so I really apologize for this. But yeah, I think I used up all the time anyway. And I say this as if this is by accident, but I actually planned this. I wanted to use up all the time because from my experience, whenever there are questions, I get very nervous. So, so there's no time for questions. However, if you would like to talk about this stuff, then it is anyway better to just talk directly. And so if you have any comments or you'd like to learn more, then let me know. And let's have a chat afterwards. And for that, there's absolutely no problem. Thank you again for coming, and I wish you a nice evening and nice rest of the conference. I think that's everything. Thank you.